I think there is something about a bit profound which I don't know how to answer. Okay, honestly, um, is why it's so rare to have such disruptive ideas coming out. Why it's such a rare event. And it makes always me think about the invention of planes. Airplanes.
Hmm.
Okay, people have been able to make gliders for thousands of years. That was not that complicated. Okay,
Mm-hmm.
just glider, not a plane, but a glider.
Mm-hmm.
Okay, and people have been dreaming about it and
Mm-hmm.
writing about it, but they didn't do it. So there is a big difference between dreaming and doing. And
Mm-hmm.
suddenly, all of a sudden, in the 18th century, in different countries, simultaneously, people started to build uh, gliders and airplanes. That means there is something where you switch from the dream to the let's do it. Okay, and it's the same for biocomputers. Honestly, people could have started to do this like 50 years ago. It was okay, right? Um, and people have been dreaming about it. You can find some science fiction books that describe the use of nervous tissue for computation. You see these big brains and with tubes and things that this is not a new idea. Okay, what is new is not the idea; is to try to make it for real. And interestingly, it's the same story as the airplanes. We do this in Switzerland, but we have competitors popping up in Australia, in the US, in the UK. So it's the same story. Why? Why suddenly the same invention pops and we come from dreams to trying to do it for real? This I don't know. This is a mystery.
Good morning, good afternoon, good evening, namaskar to all of the listeners of Perspective Club tuning in for another special episode. We have with us today here a very, very special guest whom I'm going to introduce in a little bit. But before that, I just want to jump in quickly to the topic. We're going to be talking about a very, very fascinating topic today, something that probably at the very outset might feel a bit disconnected to our usual topics of the future of energy or the future of mobility. But I promise we're going to tie the lines and we're going to get it there to energy and mobility. So please stay tuned in and please enjoy the show. So we have with us today here Fred Jordan. Fred, welcome to the show.
Thank you for inviting me.
For the sake of our listeners, Fred, I'd love it if you could quickly introduce yourself and probably the work that you're doing.
Well, I'm a French physicist, and I have made a PhD in the Federal Swiss Institute of Technology in Switzerland, and I've co-founded the company Final Spark, in which we are working on building the first living processor. That means a processor which is using, instead of transistors, living biological neurons.
Fascinating. And when you say biological neurons, these are the same neurons that exist in our brain, right?
Yes.
Got it. So I think a really, really fascinating topic that comes up to my mind is when you say processor, you mean that you're probably going to be using it for computing applications. So what is the main application that you are focusing on with regard to your biological computer?
I would say artificial intelligence, and more specifically generative AI. So, each time you use AI or like ChatGPT, or when you try to generate a picture or movie, whatever, okay, you are not doing this on your own computer. You are running a server remotely. It people say it's like cloud computing. And instead of using a digital server, we propose to use a biological server. So for you, as an end user, it would ideally make no difference in the result that you get, but it would make a big difference in the price that you pay.
Correct.
Because we know that biological neurons consume like 1 million times less energy than artificial neurons, which are used for processing AI. And this is what we are using for our processors, biological neurons. So we expect to have servers that will need several orders of magnitude less energy than digital servers.
That sounds wonderful at the very outset, right? Because I think one of the major or upcoming consumers of energy across nations, across countries in the world are data centers, because of this massive upsurge of AI that we've seen over the last couple of years. And the biggest blocker or the biggest hurdle when it comes to building more data centers is where do we get the energy to run them from? And which is why I think a lot of these data centers are being built close by or near to power plants, existing power plants, or you have new power plants coming up just to service these large, massive data centers. And when you say that you have a computer that can consume energy of an order of magnitude 1 million times lesser than a conventional computer, this sounds like the perfect solution for all of our problems. So the next logical question that comes to my mind is why is this not taken off yet? What's the big thing that's holding us back from working on this?
Well, no, well, why it's not taking off? Well, it's taking off. Okay, there are more and more companies working on this. We're probably one of the first one, if not the first one. Okay, and so it's taking off definitely. Now you have to consider that it's a bit like quantum computing. Okay. These are way of computing which are, I would say, unconventional compared to digital. And that means that we have to basically reinvent everything. Okay. So imagine like in the 60s when they invented the first solid state transistor. From there to having a computer, it took some time. Okay. So we have to do the whole journey again here, basically from scratch. The only thing that is encouraging, I would say, is that we already know that we are going to be successful, 100% sure. And the reason for this is that you and me, we are discussing right now. We are exchanging and processing information, right? Successfully, I hope. This with all your listeners. And we are actually using our very own biological neurons successfully. Okay, so that works. Okay, we just have to reproduce something which is already known to work.
That's a fantastic answer, and quite unexpected at that. And apologies for my lack of knowledge in the sense that that I didn't know tons of companies are coming up in this field. When it comes to energy, speaking on the future of energy at the moment, we look a lot at renewable sources of energy. We're looking at solar power, wind power, all of course supported by battery energy storage systems. The one big talking point when it comes to these energy sources are that they're not perennial, or they're not long term, in the sense that you have solar energy when the sun's up or wind energy when the wind's blowing. Even with the best of batteries today, you can probably hope for a buffer of about 2 to 4 hours. How do you propose that we run these data centers on biological computers non-stop, 24/7, 365, on, let's say, an energy grid that's supported primarily by renewable sources?
Well, you will have the same requirement of non-interruptible source of energy. Okay, this we need for sure. Okay, but the difference is that if you consume 1,000 times less energy, for instance, where you had a problem before, you don't have a problem anymore. So think about light bulbs. Okay, like 15 years ago, when you wanted to have light, you consumed a lot of energy, and then LED light came. and lighting energy, well, disappeared, or the problem disappeared. Not because we found more sources of energy, but because at the root of the problem is the efficiency of producing light increased by several orders of magnitude. And this is another way to solve problem. Is not to multiply the sources of energy, sometimes is to be more efficient with the energy that you already have.
That's truly a wonderful comparison that you did there. I think we've seen the evolution of lighting over the last 50, 100 years. And if what you propose is true, we're going to see the evolution of AI-based computing, or exactly the base underneath AI. And I think that this is going to evolve at a rate faster than that of lighting, for example. Like you said, lighting has evolved, let's say, over 50 years. But what you're proposing is, let's say, more short term. So my next logical question is, what would you see, for example, 5 years or 10 years into the future from now on? What kind of a market would we have for such biological computing? Would they completely have overtaken conventional forms, or do we see a good mix of both conventional as well as biological computing?
There is going to be a good mix, as you said, okay? Our competitor, I would say, is Amazon Web Services, for instance. Typical example of a big computing center, okay? Those ones which are running AI, I predict that in the 10 to 15 years are going to be progressively replaced by biocomputers like the ones that we are doing. Mm-hmm. And it's not an ideological choice. It's just capitalistic. It's just more competitive. Because if you can provide the same service with consuming hundreds of times less energy, the market is such that it will go to this kind of biocomputers.
We asked this question to a lot of the guests on the show, and I'm really tempted to ask you the same question as well. We sort of threw our guests into a scenario where in the future sometime you are the power minister or the energy minister for the entire earth. You have a choice that you would like to run your nation or the earth as energy efficiently as possible, with as less of a carbon footprint as possible. And I'm pretty sure, knowing you, you'd have biological, or exactly biocomputers at the front of your mind. How would you see a vision? How would you see a future that is dominated by biocomputers? Do you see more of a single biocomputer, that's a single mega biocomputer that's being used for the entire earth, or do you see more of hybridized, diversified microservices or micro centers running across the earth filled with such biocomputers? Or in general, what would your rollout strategy be for biocomputing if you were the power minister of the earth?
Well, these are going to be big centers. Okay, this is the most rational approach, because you have to set up some microfluidics, a number of systems. Okay, and from a price perspective, you're going to have a better amortization if you centralize this in one area. Okay, for your computing center. It doesn't mean that in the long term we could not have also personal biocomputer. Okay, and it often happens this way actually. Okay, to have a server side and then client side computation. But I'm just sticking to what the simplest model is, to have big mainframes, and that means you have to imagine a nervous tissue made of human neurons, like 10 centimeters thick, 100 meter by 100 meter. Hundreds and hundreds of billions of neurons working to serve people and processing information 24/7.
And would you also see future applications in the mobility space for such biocomputers? I'm really excited or curious to hear what you think about that.
So, I want to talk about Mr. Shockley. Mr. Shockley is a guy who invented the solid-state transistor like 80 years ago. And now you're sitting here and you are asking me to make a prediction of what is going to be the use and the way of using biocomputers in the future. I can tell you for sure, Mr. Shockley did not imagine that his invention would be used to make smartphones and connect to the internet. Impossible. Okay. And the same way, likewise, it's for me. Okay. I'm totally unable to imagine the span of the application. What I know is that it's going to be a new industry. I see the most obvious thing, but I may miss a lot of things. In order to answer your question about mobility, for instance, you know that one of the big challenge, for instance, is integration of information when you're driving a car automatically, right? And artificial systems are struggling to do this in real time. Okay, this is complex integration of information, but human beings are doing it quite well and far superior actually compared to artificial systems. We are using in our biocomputers nervous systems also. Okay. So what one could imagine, okay, that we could potentially onboard some of these biocomputers in vehicles, okay, for navigation purpose and integration of what are all the hazards of driving a car, integration of all the information that you do when you do it manually.
Elaborately and yet succinctly explained. And it's really exciting to see that the applications are as diverse as what we think, as they're only limited by our imagination, right? As you mentioned, nobody could have imagined such a wide array of applications for the transistor 100 years ago. I was reading a book a couple of days earlier. It's called Scale. Don't remember who the author was, but it's about essentially how, as things grow bigger and bigger, the energy consumption also scales down. For example, take a dog versus a human being versus an elephant. As the size gets bigger and bigger, the heartbeat, for example, slows down. The amount of blood that's being pumped, for example, slows down. So biological systems have found a way to and it's fascinating that they've found a way to sort of linearly scale down their energy consumption as their size goes up. Something about the 1/4 power scaling or 3/4 power scaling laws or something like that. Do you also see a correlation between this, what I explained, and biocomputers, that as biocomputers, for example, scale up in size, their energy consumption goes down? And does it seem a bit? It does seem a bit out of the blue, but I would love to take your opinion on this.
So first, when I answer to questions, there are many questions which I already know the answer. Okay, and this one is an original question which I never had before. so now let's talk about improvisation.
We get it right once in a time. Yeah, we get it right sometimes.
And so I can, I see a number of reasons why I'm going to be more power efficient if I've got a big center compared to a small center. This is based on the only energy that we are using right now is basically keeping the tissue at 37 degrees and providing nutrients with microfluidic pump systems over the tissues 24/7. Okay, and fundamentally, I'm not going to linearly need to scale the pumps and the infrastructure to keep the heat. I'm going to be more efficient if the system is bigger. So there is some analogy with what you said compared to elephants and insects, for instance. it seems that valid, but realize that this is pure improvisation. I have no studies or publication to back up this statement.
Got it. But this is probably a fascinating topic that I overlooked myself. Backtracking a bit, you mentioned that you'd have a system where you'd maintain these computers at about 37 degrees. They're basically comprised of neurons. You also mentioned that you had sheets that are about 10 centimeters thick, 100 by 100 meters of area. What are the space requirements for such computers, especially now you mentioned big biocomputers? How do they compare with conventional data centers?
So first, you have to make the difference between the project that we have in mind. This is the big tissue that I mentioned, and what we have right now. Okay, this is not at all at the same scale. I was talking about the future. Okay, because right now we have very small nervous tissue like this size. Okay, and we perform the experiments on this. Okay, but I mean, roughly speaking, I expect the computing center, the biocomputing center, to be of the same size of the current compared to the current digital centers.
Got it. And you more or less see a future where these computers operate independently, right? So they have minimal or no human oversight whatsoever. All you do is essentially make sure that the input constraints, that is the temperature and the nutrients, are maintained, and that's it. That's pretty much it.
Well, I think again, it's going to be similar to digital centers. And digital centers, computer centers today still have some human beings, monitoring operations. Okay,
True.
So there will be also human beings to monitor operations, even though they are biocomputing centers.
Got it. And thank you so much for the enlightening conversation on biocomputing. I also quickly wanted to delve a bit more into your past. You mentioned that you're a physicist and you've done your PhD, but I want to delve a bit deeper onto the problem statement that you saw when you came up with this idea, right? You mentioned that you were also, earlier when we were speaking, that you'd also come across a couple of papers or have written papers on your own about the topic. So what really led you to discovering this topic?
Well, first, I wrote my first publication when I was very young about artificial neurons, artificial neural networks, and then about their mathematical properties. Okay, like I don't know, 35 years ago, so, as a student, just for fun. But what happened is that when we created Final Spark, we didn't think about biocomputers, not at all. Okay, what we wanted to do is a revolution in AI. That was clear, but we were two. and at the same time, you had Google, big companies spending billions. Okay, but we still believed that we could make a difference. But there was one condition. Okay, very clearly not following the path and the footsteps of the big ones, because we would always be late. So if people were running this way, we decided to run, orthogonal way. Pursue only direction of research in AI which have not been followed by the big ones. And one of these direction of research was, instead of using standard artificial neurons, as you know, this is what is used in AI, we decided to use so-called spiking neurons, which is another artificial type of neurons, so simulated neurons, but way more sophisticated. And then, after a number of years, we realized that the power consumption of these more sophisticated models of neurons was so high that we were consuming kilowatts of power on the server we bought for simulating a few hundreds of neurons. At the same time, one of our employees was working on biological neurons, human biological neurons. Then, just by discussing internally, we realized that we didn't have the right solution, just from an engineering perspective. Because if we consume kilowatts of power for a few hundreds of neurons, and we need billions of them, it doesn't make sense. It's like you. If I want to simulate your brain, today I would need like a small nuclear plant. Okay, it's not realistic. It's not the right way.
Absolutely.
So it was really a pragmatic, it's approach, very simple, prosaic. Okay, so it's this. It's already existing. These are biological neurons which have been optimized by hundreds of millions of years of evolution. And evolution was only concerned by one thing: efficiency, power efficiency. So let's use what has already been optimized and put it as an element of our processing system.
Got it.
As simple as it is. It was very simple approach.
Simple yet elegant, and I do realize that it's taken you a lot of time, right? So this isn't something that you happen upon, let's say, a day, or most probably it is something you happen upon a day, something that sort of strikes you as a flash of inspiration. But in order to reach that point, you do have to do a lot of work, and then we've seen that it's 35 years of effort that you've put in. But we here in the Perspective Club have most of our listeners are also young energy professionals or young enthusiasts wanting to break into the energy and mobility space. And most of us usually are either in the search of good quality companies working on quality topics, or are in the search of the next big thing, next big idea. For such of us, we could definitely use enlightenment from people like yourself. So what ideas would you suggest are still out there to worth exploring, not in the sense of oh, okay, I'm gonna build myself the next competitor, but what topics do you think are still worth exploring out there, especially in the field of computing and energy, and what advice would you give in general to such young enthusiasts?
I think it's very good to read science fiction books.
Oh, okay.
Okay, I never go to sleep without reading some pages of science fiction. Okay, I think it's good. It opens the mind. Okay, and I think it's good. I know in this world, it's people don't like to dream too much, but it's good to dream about things that to think differently. So, and think differently, that means you let your mind dream about what really inspires you. Okay, what has never been thought of, never been done. This is, I think, the most exciting things. So it's good to think in a way it's different. So at the end, you become different.
Oh, yeah, true. I mean, I've seen in the world two big groups of people. One who they say is, copying is the biggest, sincerest form of flattery, and the others who say really, really push yourself, out there to beyond what is known. So I do know that which group of people you fall under. And since you mentioned it, is there any recommended reading that you'd advise?
Well, I read either scientific publication, okay,
Yeah.
and or I mean Arthur C. Clarke, for instance, if is for me the reference in the spirit of also optimism related to technology.
Got it.
There is a sense today that technology is bad, okay, and I think this doesn't lead us in the right direction. Okay, technology can be good for the human, and I'm happy to be today and not 2,000 years ago. We
Yep.
live way more, and this is thanks to technology. So we have to be thankful to this and bet that with technology we can make even a greater future.
Got it. And on that note, I'd love to wind down our conversation. You've definitely given us a lot of inspiring thoughts and words to think about, to ponder on, and a fascinating topic to watch out for in the coming years. And so I thank you so much, Fred, for giving us your time today.
It was a pleasure, particularly with interesting questions, which I have to dig in a little bit more.
we'll give you the time before you come on to our show for another episode for a follow up. But on that note, to all of our listeners, thank you so much for tuning in to another episode of the Perspective Club. Be sure to like, share, and follow us on all your channels: Instagram, LinkedIn, Facebook, Twitter. And please do check out Fred's profile as well. We'll be linking that on the show notes. And to all of you, thank you once again. And be sure to tune in for another episode of the Perspective Club. See ya.
Well, no, if you're on the was like, I mean, the words don't come from me actually. It comes from an investor I was discussing with,
Hmm.
and he said basically, biocomputing is not simply another technology; it's a new industry.
Hmm.
I didn't think about this myself. Okay, so I
Yeah.
was surprised. How can this guy who doesn't know about biocomputing as I know has a vision better than me? So, wow, okay, I'm going to keep this vision for me because it's interesting. So, I think there is something about thinking out of the box,
Yeah. Yeah.
for and this may also be true for future energies.
Hmm.
Uh, and it's way easier, okay? And I tell you as an engineer, okay?
Hmm.
Uh, Refine something that already exists, okay? It's a different thing to start with something totally off, of course. But this is where really happens the big progresses when you
Hmm.
disrupt,
Yeah.
totally. Okay. But I don't know how to generate this this kind of invention process in a predictable manner. It seems to happen quite rarely. So.
Maybe AI can help us with that. Let's see.
You're
Oh,
welcome.
biocomputers, right? Yeah. Um, oh, just confirming with you. If that's okay.
Yeah, that's okay. Well, there is something I'm interested in.
Hmm. Go
This
on.
is much more down the earth. Okay.
I'm all ears.
Yeah. We are also looking for money. Okay. And we want to raise 50 million of dollars. Okay. And with the first one at 10 million, but ideally 50 million. Okay, all at once. Okay. And this is one of my objectives also by communicating around biocomputing, so to get some funding to keep on doing this research because we need a lot of people to work on this simultaneously.